I'll go live on YouTube now. Okay. Hi everyone, thanks for coming to this week's seminar. Just to give a quick overview before we begin, we'll have a talk for about 40 minutes, so please keep mics muted during this time. This talk is being recorded and live streamed to YouTube, just so you're aware. And we'll have time at the end for questions. So please either, if you're on Zoom, raise your hand and ask your question on the video, or type your question in the Zoom chat. If you're watching on YouTube, please put your questions in the YouTube chat and we will ask them on your behalf. The seminar schedule for our remaining seminars is shown on the link there. But now I'll pass you over to Leo, who will introduce today's speaker. Thanks for coming.
All right, thanks, Caitlin. And it's my pleasure to introduce you to today's speaker, Dr. Seogi Kang. Seogi completed his PhD in geophysics at the University of British Columbia in Canada in 2018. His thesis was focused on computational methods for electromagnetic geophysics applied to mining problems. Currently, he's a postdoctoral researcher in the geophysics department at Stanford University. Seogi is a core contributor to the geosci.xyz website. That's a vast resource of open educational content, and also the co-creator of the widely used open source geophysical software SIMPEG. His current research focus is on maximizing the value of remote sensing techniques like InSAR for groundwater management and groundwater science in California. And it's with that, I'll hand it over to Seogi for a very interesting talk today.
Thank you very much, Leo. So I'm going to share my screen quickly. And let me see if I can minimize this. Okay, oops. Can you all see my screen? Is that working? Leo, is that working?
Yes, it is.
Perfect. Yeah. Thank you so much. Yeah, thanks, Leo, for inviting me as well as introducing myself. And today I'm going to talk about monitoring of the groundwater system using remote sensing technique in the Central Valley of California, USA. As you can imagine, this is a really big topic. And kind of a warning, I'm not necessarily going to solve this problem, but I'm going to show two pieces of the puzzle today. And at the very end of this talk, I will sort of complete the kind of full picture, how we can potentially monitoring the groundwater system using remote sensing techniques in the Central Valley of California. So that's my goal. So I'm going to start with like a kind of this picture of saying water matters. And there's probably no question water matters for not only for us, but also for the entire ecosystem. So it's kind of worthwhile to think about where we actually get water. And one of the major sources is the surface water, like a lake. So I think I actually Googled today what is the major source of the Liverpool, and it's Verney, like a Verney lake, and there's a dam. So you can imagine that dam. So this is an image of the Lake Oroville in California, Northern California, USA. And this is the picture at a wet year, means what the wet year means, there's enough precipitation. And probably in Liverpool, it's always wet year, but in California, there's a wet year. There's also a dry year, okay, depending upon the amount of precipitation. And that's the figure. And in this situation, we have enough surface water that can be used for various purposes. It can be used for municipal use, drinking water for domestic, and irrigation water for farming. Okay, in this situation, we may not have any problem. But things can go wrong in a different year. So this is another image, but the same place in 2014. And this was a drought year, meaning there was not enough precipitation. So you can see the bottom of the lake. So clearly there's there's not enough water that can be distributed for various purposes, while the demand of the water in the region stays about the same. So, and that's where we're kind of facing the problem. In this situation, where can we actually get water? And water is another question is, what is the other source of water than surface water? So it is the groundwater, which fills in the pore space of sediments and rocks like this, So this blue part, you can kind of imagine that's the pore space, and they are filled with water. And importantly, the groundwater occupies 97% of all liquid form of fresh water, so which is a large amount, but it is finite, right? So because it's finite, depending upon the population growth and climate change, there's a potential that groundwater resources can be depleted, meaning there could be an issue related to groundwater sustainability. And this groundwater sustainability issue may not be kind of like really big in the Liverpool, I guess in UK in general, but if you move to a place like California in Western US, this is a really serious problem. And you can actually feel it on your skin. And these are the images. If you drive from so I'm located in the Bay Area. You may not have geographic location of California. If Bay Area is at the Northern California, and the LA is at the Southern California, and the Central Valley is in between. So if you actually drove from Palo Alto, Stanford to LA, those are the sceneries that you can actually see. And the farmers are saying there's no water to be used to grow their crops, like almond trees, for instance. And some of the farmers are actually ripping apart their trees like this because there's no groundwater or any surface water that can be used, or it's just too expensive for them to buy those water. So this groundwater issue is really, really serious in Western US, especially in the Central Valley of California. So we need to do something for sustainable groundwater management. And for this sustainable management of groundwater resources, we actually need to have an ability to monitor groundwater system, like groundwater flow and volume. And if you think about the scale of this problem, the typical size of the water basin is about 50 kilometer by 50 kilometer area. And the depth scale is about hundreds of meters. So kind of monitoring this large system, it's extremely challenging task. And sometimes people forget about this. Actually, for monitoring of the groundwater system, you need to understand what is the hydrogeology of the subsurface under the ground. So you need to understand what is the conduit of the flow, what is the barriers of the flow, because that actually determines the volume and the groundwater level, changes in volume and groundwater level change. So that's another kind of challenging task. Again, this image is actually not available. So again, it's a big area and we need to see through hundreds of meters of depth. Okay. So this is an extremely challenging problem. And okay, it's challenging, but the question is, what is then traditional sort of approach for these challenging tasks of monitoring and imaging the subsurface? And it is well-based approach, basically drilling a well. And as you can imagine, you literally drill a well, and what it can provide is a very accurate point information. And it can also provide a direct information about the hydrogeology or lithology for imaging. And it can also provide a groundwater head or groundwater level. It's an elevation of the groundwater. And on the other hand, it's somewhat surprising, but the well data, the quality of the well data, it's actually variable. I'm not sure that's the case in UK, especially in California. If you have worked on well data, the quality actually depends upon the well. It varies a lot. So sometimes it's actually, you cannot really assume the well data as a ground truth. Okay. And more intuitively, the spatial density of the well data are relatively low. So there's a kind of, if you think about the separation between well, that's pretty large, at least like a couple of kilometers. And if you think about the dimension in depth, the coverage of the well data is generally decreasing with increasing depth due to the increasing drilling cost. Because think about drilling a well at a deep part, it'll be more expensive compared to the shallower part. So these kind of disadvantages generate a large data gap between wells and at the deeper part of the subsurface for monitoring and imaging tasks. So what I'm going to focus on today is what can be an alternative approach for this? And I'm going to use remote sensing techniques. I'm going to use, there are many different remote sensing techniques, but I'm going to focus on two. The first one is the satellite interferometric synthetic aperture radar called InSAR, measuring surface deformation. And the second one is the airborne electromagnetic method. for imaging. So let's start with the InSAR for monitoring groundwater head. So here's our satellite, and you can send the electromagnetic pulse with some sort of wavelength, and then it'll hit the ground and come back. So you can actually measure the phase between the satellite and the ground. And the satellite can kind of go around the Earth orbit and come to the same place, actually can send the pulse again. And what it can provide is this phase difference, gives you information about the surface deformation in time, okay, at the 2 time interval. What's kind of cool is the spatial and temporal changes in groundwater head are encoded in this ground deformation, which results in surface deformation that can be measured by this InSAR technique. And as you can imagine, InSAR has a great spatial coverage, basically seeing the Earth's surface, covering the Earth's surface, and high spatial density, about 2200 meter resolution, and good temporal sampling rate between 6 to 12 days. And importantly, it is sensitive to the head in the deeper part of the aquifer, likely confined or semi-confined. So it has a chance to fill in the data gap at the deeper part of the subsurface. But on the other hand, every methodology has a kind of limitation. So it is critical to understand what is the limitation of the technique. And InSAR, what it provides is an indirect information about the head. So what we're measuring is the surface deformation, but not the changes in head, okay, groundwater head. And also there are other factors of kind of can generate the deformation, like hydrologic loading. There could be tectonic activities that can contribute to the deformation. So it is critical to, when interpreting the InSAR data, it's important to kind of like separate different signal. Okay, this signal is related to the head, but this signal is not necessarily related to the head. So that's the important part as well. And that's the challenge. And the second technique that I'm going to use, an airborne electromagnetic method for imaging the subsurface. And like I'm not an expert actually in the InSAR, but I'm an expert in this electromagnetic method. So I'm kind of in the learning at the sort of the learning curve, learning other kind of remote sensing technique like InSAR, but this is my kind of core expertise. So here's our helicopter, and there's a big loop. It's about 10 meter radius. So it's actually a pretty big loop, the size of a room. And then what we do, we kind of inject the time varying currents, and that'll generate the time varying magnetic field. And this time varying magnetic field will induce the currents at the subsurface. Because if you think about the air is an insulator, so there's no currents flowing, but the subsurface materials are a conductor, so it can actually conduct the currents. There will be a large signal generated in the subsurface, and we can actually measure corresponding secondary signal at the receiver loop located here. And as you can imagine, the typical speed of the airborne EM method is about 100 kilometers per hour. So obviously we can rapidly map out large area. So it kind of usually a size of a water basin in California, it takes about several days. And importantly, it is sensitive to the large scale feature like the regional confining layer, top of the basement that could act as that could provide an impermeable base of the groundwater basin, but not necessarily very fine scale features like 1 centimeter thick clay. We don't have like a big chance to see that, but it is very sensitive to the large scale feature. And again, it is important to understand the limitation of the methodology. So what the AEM method provides is an indirect information about electrical resistivity of the subsurface. So if you think about what we are capturing through this EM wave propagation is a variation or contrast of electrical resistivity in hydrogeologic units. So it is critical to understand the relationship between electrical resistivity and hydrogeology. Again, we're not seeing the hydrogeology itself, but the electrical resistivity. So we're hoping to see the hydrogeology through the electrical resistivity. And the second limitation is like the resolution. And the resolution of this method actually degrading with depth. As you go deeper part of depth, the resolution gets worse and worse. And that is related to the diffusive nature of this physics of electromagnetics. So kind of, here's my kind of overarching question. Like, so we have these two remote sensing technique, InSAR and Airborne EM. It has some advantages and some disadvantages. And we also have in-situ well data that has some advantages and some disadvantages. And like my overarching question is like, how do we then integrate this modern remote sensing data and traditional well data or in situ data to monitor groundwater system with high spatial and temporal resolution? Okay, that's my overarching question. And today I'm going to focus on Central Valley of California. And here's our Central Valley of California, this yellow region. And this is a Pacific Ocean. And this is the Sierra Nevada, if you're not familiar with the California. And the Bay Area located here, and LA is somewhere here. The Central Valley of California is very productive farmland. That means to maintain that productivity, agricultural productivity, it uses significant amount of surface water as well as groundwater. And in 2012 and 16, there were severe droughts in California, which have drastically increased the amount of groundwater pumping in this region, threatening the groundwater sustainability in the Central Valley of California. Reflecting that, Californian government in 2014 legislated a Sustainable Groundwater Management Act called SIGMA. And with this act, there are many different regulations about groundwater level, groundwater volume, subsidence, as well as the water quality. And this kind of shows the intensity of the groundwater issues in the Central Valley of California. So it is a really serious problem affecting the people living in this area. The Central Valley of California can be divided into sort of the two different regions. The northern part called San Joaquin Valley, this part, and the southern part, Sacramento Valley, and the southern part called San Joaquin Valley. So this southern San Joaquin Valley has the climate is much warmer and drier compared to the north. And this kind of induces more pumping of groundwater, and more pumping of groundwater cause more subsidence. And this is the map of subsidence between 2015 and 19. So it's a 5 years of ground deformation or subsidence. And the red color means about 130 centimeters. So it's about 1.3 meter. So if this is like about 5 years, it's about 25 centimeters per year, which is a huge amount of subsidence that we're getting. And if you think about this subsidence, it can actually make a huge damage for infrastructure like a railroad or canals in Central Valley, which kind of deliver surface water to various different locations. So this is actually a serious problem as well. But the subsidence means there's we're losing the kind of the storage of water permanently. And that's another set of problems related to the groundwater sustainability. So it's kind of that's the problem. And it's worthwhile to think about what is the aquifer system of the Central Valley. So Central Valley aquifer system is composed of mostly sediments like clays and coarse-grained material like sand and gravel. And this is kind of conceptual figure showing that. So yellow color means the coarse-grained materials like sand and gravel, and this dark brown color means the interbedded clay. So as you can see, there are numerous interbedded clays throughout the aquifer system. And the thickness of the aquifer system is about 300 meters to 1 kilometer, genuinely increasing towards the center of the valley, which kind of makes sense. And if you go to the southern part, San Joaquin Valley, there is a regional confining layer called corcoran clay. This divides the aquifer system into a shallow unconfined aquifer and deep confined aquifer like this. And this, a red contour, is outlining the lateral extent of the corcoran clay. And what's interesting is the large substance anomaly, which is this red color, is mostly included in the lateral extent of the corcoran clay. And that kind of gives us a clue. The major source of the ground deformation is due to this deep confined aquifer. And this regional confining layer, corcoran clay, plays an important role because that actually generates a pressurized system that can generate a large amount of ground deformation. Okay. But even beyond this region of San Joaquin Valley, much of the Central Valley aquifer system is best described as a semi-confined system, and that is mainly due to this interbedded clays. So each interbedded clay can act as a small, a confining unit. So if you have many interbedded clays, the aquifer system can act as a semi-confined or a confined system. So that was about kind of the background needed to talk about the two major examples. And today I'm going to show, first I'm going to show the InSAR in the Central Valley scale, and then I'm going to narrow down to a water basin scale using the airborne electromagnetic method. For the InSAR technique, I'm going to focus on how we can kind of extract the changes in head level, groundwater head level from the InSAR deformation. For the AEM, I'm going to focus on how do we image the subsurface hydrogeologic structure. Okay, the first case study is recovering groundwater head from InSAR surface deformation data. And available data in the Central Valley, we have InSAR data, which provides a surface deformation. And we have about 1.7 million time series, meaning we have 1.7 million locations. And the lateral resolution is about 2,200 meters, and the temporal sampling is about 6 to 12 days. So total, we have 284 time channels between 2015 and 2019. We also have head data, which kind of provides like a ground truth. And we have about 20,000 well locations, including all types of wells, not just the monitoring wells, domestic, irrigation, monitoring, municipal. And the lateral resolution is highly variable. And by looking at this kind of image, oh, it looks like we have lots of well data. And then what's actually the point actually using remote sensing data? It seems like we already have a good resolution. But if you actually look closely and then plot up as a function of time, some of the well doesn't have any data or have like a few time points. And the time span is like a time span can be very, very different. Sometimes it's just between 1950s to 1960s, and sometimes it could be 2002 to 2015. So that kind of gave us a motivation. Okay, we have a big data gap in this head data in the temporal direction as well as the spatial direction. So here's that's what we have. And the conceptual model of the surface deformation in the Central Valley can be like this. Surface deformation can be equal to total elastic response, which is related to the changes in groundwater elevation or groundwater head level, plus some loading response, which I'm going to explain later, and then plus some noise. So this is actually a fair assumption in the Central Valley, but this assumption could fail like in different locations. So I'm going to start with the poroelastic response, and that is sort of like that is the response containing the information that we want, because that contains information about the groundwater head level. So here's a simple like a conceptual diagram, and then we're going to focus on this deep confined aquifer, which is a major source of the ground deformation. And if you pump the groundwater, what happens, it reduces the groundwater head in this coarse-grained materials, okay? And I'm going to call that as H coarse. And what happens, because of that, there will be a head gradient between this clays and the coarse-grained materials. And that will drain, this head gradient will drain the water from clays to the coarse. And this process will compact the interbedded clays due to the head changes in the clays. And the reason why the compaction is happening mostly in the clays is due to the compressibility of the clays. The clay compressibility is much greater than the coarse-grained compressibility of coarse-grained materials. So to summarize, the driving force of surface deformation is the head change in the confined aquifer, or more like concisely, the coarse-grained materials. But this surface deformation is modulated by interbedded clays, the properties of interbedded clays. And given this is the core process, I'm going to dive a little bit deeper into the physics. And why we're having this ground deformation is basically due to the stress. Okay, so the total stress, sigma T, can be written as sigma prime, which is an effective stress, plus pore pressure. And if you're assuming this, the total stress is not changing in time, we can rewrite this as like this. Okay, so the changes in effective stress is equal to, is linearly related with the changes in head. Okay? And that's why head generates the changes in effective stress. And we can kind of, the deformation, which we're interested in, can be written as like this. So deformation is linearly related with the changes in head, and the property called the skeletal specific storage, SSK. Okay, and the B naught is the initial clay thickness. But bottom line is the deformation is linearly related to this parameter called SSK, specific skeletal specific storage, as well as the changes in head. Okay. And like what's kind of fascinating physics behind is you think about if everything is elastic, although clay can have large compressibility, if everything is elastic, there shouldn't be a large subsidence happening in multi-years, right? So it'll kind of go back and forth. But what we are seeing is a permanent subsidence. And the reason why that's happening due to this hysteresis. So here what I am plotting, x-axis, you can think that as an effective stress or reducing head. And then the y-axis in this direction is increasing subsidence. So when the head level is increasing, so you can kind of think that as a recharge event. And it kind of follows this curve, which is the slope is not too high, okay? But for reducing head, the slope is much steep, right? And if we make a linear assumption, we can rewrite this as like this. For the elastic case, it follows this, the slope of SSKE means elastic. And for the reducing head, it follows the SSKV, which means inelastic and permanent loss. And the important part, SSKV, which stands for this inelastic subsidence, inelastic deformation, it's much greater than this SSKE, which is the elastic part. And this imbalance generates the large subsidence that we're measuring in the InSAR data. And another interesting thing is the head in the clays are delayed. So again, when we pump the water, it reduces the head in the coarse-grained materials, and that drains water from clays to coarse. And this is a diffusive process which takes time. And the governing equation is like this, okay? And this time really depends upon the hydraulic conductivity of the clays as well as the skeletal specific storage. And with this delay, what we're seeing is so there will be a delay between the head in the clay and head in the coarse-grained materials. And effectively, that generates the compaction of the clay with this equation. And that results in delays between the head of the coarse-grained materials and measured compaction or measured subsidence with the InSAR. So that's another interesting physics behind. So that was it. That was basically explaining what is the poroelastic response. And the second response is the loading response. It's much simpler. So if you're adding water onto surface, you can think about any form of liquid like snow, water, ice. And if you add the mass onto the surface, it'll generate the subsidence like this, okay, due to the increased mass. But if you remove the mass, like if you think about the drought period or dry season, you're removing the water, it'll generate the uplift. Okay, so that's another kind of response. But what we're measuring is a summation of poroelastic response and loading response. So it is important to separate these two if you want to monitor the groundwater, the changes in groundwater head using the InSAR surface deformation data. So that's the motivation of the data analysis. So the question that we have, how do we kind of separate, or how do we even we know what is poroelastic response and what is loading response? Okay. And then what we want to see is the relationship between the head and the InSAR surface deformation data. Can we see expected correlation between that? So those are sort of two major questions that I want to address. And again, InSAR data, as I said, there's 1.7 million locations. And each location have 284 time series. So even just looking at the data and see the correlation, it's a challenging task. So the question that I'm having, can I categorize this each InSAR data location into several categories that has distinctive temporal features? And what is the technology that I can use? So I use this very kind of standard, unsupervised machine learning technique called K-means clustering. So again, what I asked to the algorithm, okay, I have 1.7 million location, classify that into 6 different clusters that has very distinctive time features or temporal features, and that is the result. So this different color means each different cluster have very different temporal features. And what's interesting, I didn't constrain any, put any spatial constraint, but by looking at the image, you can see good spatial correlation that is completely driven by the data, which is interesting. Okay. I can plot it up as a function of time by each cluster. This is cluster 1, cluster 2, 3, 4, 5, 6, and they have very different time features. So generally, the level of subsidence is increasing as with increasing cluster, but there are some interesting seasonal features happening. Okay, I'm going to go through it later. And that was one part. And the second part was we want to understand the relationship between the InSAR surface deformation and the head, right? The measured head. So to do that, we need to kind of have some sort of collocated data of InSAR and head measurements. So what I did for each InSAR data location, I draw a circle, I used 1 to 2 kilometer radius, and find the collocated data. So I'm going to have a collocated pair of data having both InSAR data as well as head data. And now I'm going to show kind of this collocated data for cluster 1. And the cluster 1 is black color. And that is the 76% of the data, which is dominant data set. Okay. And then this is the plot of collocated InSAR and head data. And x-axis is the time, and y-axis on the left hand is the head, meter above the sea level. And right-hand axis is the deformation in centimeter. Okay. And this blue color means the wet season, and white color means the dry season. And this red color means the drought period. Okay. And I'm going to start with the orange curve, which is the head measurements. So head measurements is increasing in wet season. Kind of makes sense. Got more water, head goes up. And in the dry season, it goes down, it goes up. In the wet season, it goes down, it goes up. In the drought period, it generally goes down like this. And then it recovers after the drought period. So it seems like making sense, right? And now let's look at the InSAR surface deformation data. In the wet season, it goes up. And in dry season, it goes up. In wet season, it goes down. And again, dry season goes up. And it's completely out of phase with the head data. And that does not making sense if we're thinking that as a poroelastic response due to the head. So if you think about the other response, the loading, in wet season, we're expecting, in the dry season, we're removing the mass. So the ground elevation will go up, right? So that kind of makes sense. In the wet season, we're pouring the water onto the surface. It'll make a subsidence like this and then oscillate. So it is obviously due to the loading effect. And that's why we kind of determine, oh, this data, cluster 1 is dominated by the loading effect. In cluster 2 to 6, what we see is a large amount of subsidence. And given severe droughts in the Central Valley, large subsidence, it's hard to be the loading effect. Because if this was the loading effect, what we were supposed to see is a large uplift, but that's not the case. So it is clear that this large interannual subsidence is due to the poroelastic effect. So we determined that cluster 2 to 6 are mostly dominated by the poroelastic effect. Okay, so now I'm going to show the collocated data for cluster 3, 5, and 6. So cluster 3, it's following. And again, if I'm starting from the head data, in a drought period, it generally goes down like this. And after that, it kind of recovers. And if you look at the InSAR data, it kind of you can see the delay. It's very similar, but that the peak is delayed. And that is exactly because of that diffusive process. So the head measurements at the coarse grained materials will be and then InSAR data, there will be a time delay like this. So we can see the correlation. And I want to emphasize that the head recovery between this 2006 to 18 was 80 meter. And there was no a known recharge event. So it's what's called in lieu recharge. So people probably just stopped pumping. And that was the amount of recharge that we were able to obtain, which is kind of really interesting part. Cluster 5 is the red color here. And that was the location where we have seen the big subsidence anomaly. Okay. And again, I'm going to start with the head data. So kind of head data oscillates with the seasons. And in the drought period, it genuinely goes down and it goes up. Okay. And that's what's happening. And if I look at the InSAR surface deformation data, when the head is going down, it's genuinely going down, which kind of makes sense. But although in this period, head is kind of going up or stabilized, the substance is still happening. And with the increasing head, lots of increase, it kind of plateaued and slightly decreasing. So not necessarily like a increasing head, not necessarily, or even plateauing, a stabilized head does not really stops the substance. And that is mainly due to this this delaying process. So the head drop happened in the past actually makes an impact of the substance and the current status. So you actually need to understand this physics to understand what is the surface deformation data and then what is in relation to the head. And again, with the decreasing head, it goes down, and increasing head, it kind of plateaued, but still decreasing. Okay. And the cluster 6, it's another kind of interesting one. So we're seeing the large level of substance, but there's a large oscillation like this. And if you look at the head level, there's a large oscillation. So currently, our hypothesis is mainly due to the large level of head oscillation, as well as a large amount of clays. That's our current hypothesis about this. Anyway, the bottom line, like there are interesting features, temporal features of the substance in the InSAR surface deformation data. So summary of the data analysis, cluster 1, the 76% of the InSAR data were dominated by the loading effect. And so we need to somehow remove the loading effect, because what we want is extracting the poroelastic effect due to the changes in groundwater head. In cluster 2 to 6, we were able to identify strong correlation between the head measurements and the InSAR data. And that's kind of give us a bit of promise for monitoring groundwater level by using the InSAR technique. And I'm going to be very brief about this. So at the end, what we want to recover, what we want to do is estimating the head of the coarse-grained materials in this deep confined aquifer from the measured InSAR data. So the forward problem is for a given head in the coarse-grained material is estimating what is the InSAR data look like. But what we want is actually going backwards. For given InSAR data, we want to estimate that can fit the InSAR data we want to estimate at the head level that can fit the InSAR data. And obviously, we need to know the properties of the clays like hydraulic conductivity, thickness, and volume fraction, which is unknown. So that's another challenges that I am faced. And I'm going to show one sort of a simple example of showing the proof of concept. So I picked a location that other people like the Smith and Knight researched about the similar topic, but they have used both InSAR data as well as the head data. So they were able to estimate the geomechanical properties of clays. So I have used the same properties. So I don't really need to worry about that. So what I did, I picked a location and drew a circle of 3 kilometers. So and this is the InSAR data within that circle. And I take the average, which is this black curve, solid black curve, and I'm going to consider it as a data. I'm going to invert that to estimate what was the required a level of head change. And here's my kind of small experiment. So this yellow orange curve shows the initial head that I have assigned for this inverse problem. And this black curve shows the observed InSAR data. The goal is finding changes in head that can fit the observed InSAR data. So that's what I have done. And this is the head level, the changes in head level that I was able to estimate. And I was able to fit the InSAR data. Okay. And just by looking at this image, we may not have much idea, is that really good? Is that really meaningful? So that's where we need the co-located data. So this co-located data was actually close enough to this location. And we can actually compare what we were able to estimate and with the actual measurement at head level. And at the period where we don't have the InSAR data, we're doing a relatively poor job. But as we get closer to the time period where we have InSAR data, we're actually doing a pretty good job. So it's increasing here, increasing, and going down, and going up, and I've used about the same scale. And it's going down and up. It's kind of like a plateau, but we don't have samples here, and likely this could be the case. Going down and going up, and this chart we don't have the head measurements, but we do have InSAR data, so we were able to estimate the head level. This actually shows kind of the potential of recovering these changes in head level from the InSAR data. And that was sort of the summary of like we showed the potential to utilize the InSAR data as a tool to monitor changes in the semi-confined and confined aquifer in the Central Valley of California. And so it was cool to show one location, but the goal is actually extending to the entire Central Valley. So then the question is, okay, what is the data gap for extending this to an entire Central Valley? So the first data gap, we actually need to know like where is the core crunch clay, presence, depth, and thickness. We also need to understand what is the thickness of confined or semi-confined aquifer system and the clay fraction within the aquifer. There are many other things. So those are sort of the major data gap that we're faced. And how do we fill in this data gap is sort of the second project. I think I'm running out of time, so I'm going to go very quickly about this. So the idea is what we're seeing through this airborne electromagnetic method is the electroresistivity. So here I'm plotting up the blue as a low resistivity and red as a high resistivity. Starting from the blue, this is the seawater. Then you can see the clays, and then sand and gravel, and the bedrock at the very high limit. But what's actually interesting, if you draw a line here, there's non-uniqueness. For a given, like a single resistivity value, we cannot really distinguish what's clay and what's in sand and gravel. So that's the general challenge that we're up against. But the fact that the hydrogeologic unit have different resistivity value gives us a bit of promise. By obtaining resistivity distribution of the subsurface, we can actually interpret or image hydrogeology of the subsurface. But that's a challenging process. And what we've done was like developing a new approach to map out the large scale structure. And in this case, we were focusing this core crunch clay, which was the regional confining unit. And we have used the Airborne EM data plus a few high quality wells for the calibration. And the key improvement that we made was incorporating prior knowledge of the target into the inversion step to improve the accuracy of the inversion. Yeah, so I'm going to go, and the reason why we were motivated, like there's a large scale AEM project ongoing in California. And so by generating the technology, developing the technology, we can transfer that technology into many different regions. That was actually the big motivation. And this was the study area in Cuesta Basin, which is located at the location where we see the big subsidence anomalies. And this was the hydrogeologic conceptual model. Here's our regional core crunch clay, divides the upper aquifer and lower aquifer. And that's the target that we want to image. And sort of the features of target, like we're expecting a large resistivity contrast between the clay and the surrounding aquifers. And the thickness of the clay is supposed to be much smaller than the thickness of the aquifers. Those are the two kind of the prior knowledge that we want to incorporate in the inversion process to improve the accuracy. And we have available data, AEM data, Airborne EM data, acquired in 2018. That's the black dots. And we also have this high quality well data, well A and B and C, which we'll use for the calibration process. And what we're using as a technology, because we measure the Airborne EM data, which is about 50 maps like this in a large area. But we want to find is a resistivity distribution that can fit this large amount of data, and this technique called inversion. And I developed this technique under an open source geophysical software called SIMPEG, which Leo mentioned in the beginning. And if we use kind of a conventional inversion approach, and that's the image that you can obtain. So it's actually not bad if you compare this groundwater model from many well data, compare if you compare that with this 3D resistivity model from Airborne data, we're seeing a lot of commonality in between two images. You can see the clay, upper and lower aquifer, low permeability sediments with clay reach, and high resistivity bedrock. So it's actually not bad. But if you zoom in, that's the vertical section of a flight line. And what we see is kind of very smooth, like layer boundaries, and very thick Corcoran clay, which is about 100 meters thick. And that is not what we're expecting. From the well data, we're expecting about 20-meter thick Corcoran clay layer. So it is okay, but somewhat wrong. So the question was, how do we improve this kind of accuracy of the inversion? And that was the motivation to develop this targeted inversion approach. And that's what we were able to image. So what we did, we incorporated the kind of the prior knowledge of the target, which was large resistivity contrast between the clay and the surrounding aquifers. And the thickness of the clay was much thinner compared to the surrounding aquifer system. So that's what we were able to image by using what we call targeted inversion and compared to conventional. But these two images are equally fitting the Airborne data. So without any additional data, it's hard to say which one is better. So luckily, we had this ground truth data, and that was how we were able to calibrate our inversion process. And as you can see, the target inversion was much better compared to the conventional approach. And that's a three-dimensional view of the final resistivity model that we were able to obtain. It's about 40-kilometer scale, and it's showing the top 300 meter. Okay, and that's the Corcoran clay. So yeah, as I said, developed approach is readily transferred to other regions, and it can be used to develop a high-quality hydrogeologic model from Airborne data. And the question is, what's next? So obviously, we can integrate this remote sensing data. InSAR data provides hydraulic head modulated by clays, and AEM data provides information about the clays. We can integrate this in-situ well data, and at the end, we potentially want to obtain the monitoring of groundwater system with high spatial and temporal resolution. And sort of the tools that I am using to, like the technical tools that I am using to develop this technique is SIMPAC, which is an open source toolbox and framework for geophysical inversion. I'm not going to go through it, but if you have any question, I'm happy to answer. And all the research code that I have developed for my research are publicly available through this SIMPAC software. And what's actually really exciting, there is a large volume of high quality remote sensing data are coming. And for example, large scale airborne EM data in California, it'll like basically cover entire Central Valley of California with some resolution. And this is supported by Department of Water Resources in California. And the DWR also providing this InSAR data every 6 months and covering the entire Central Valley. So we have a large amount of high quality remote sensing data. And this combined advancement in sensor technology and computational power provides a quantum leap forward for utilizing the remote sensing techniques. And today I have shown sort of the two major examples using InSAR data and the Airborne EM technique, and to kind of monitor spatial and temporal changes in groundwater head, but there can be many other remote sensing data and techniques, so it can be expanded for changes in groundwater volume by using GRACE data, for instance. So it's exciting to be in this situation as a geophysicist, like we got this high quality data as well as the computational power. And my focus is I really want to maximize the value of this remote sensing data for improved understanding of groundwater systems. Thank you very much.
All right, thank you, Seogi. So do you have any questions for Seogi, either on Zoom here or on the YouTube? Yeah, so yeah, I have one actually. So for these inversions you were mentioning, it's quite a bit of data,
right?
For both the EM and the InSAR one. Did you need any kind of special large scale computing to solve all of this, or?
Depending upon the scale. So a water basin scale, airborne EM data, I just need a couple of nodes to handle that. Because it's a little bit nonsense, but what we're using is we make a one-dimensional assumption. And so for each sounding location, we do a 1D inversion. And then sometimes it's called stitched inversion or spatially constrained inversion. But that's the traditional tool. If that's the case, it's not that expensive. You just need a couple of nodes to handle a water basin scale. But if you're expanding to a Central Valley scale, you probably need to multiply, 50 or 60, because there could be a 50 to 60 water basin in the Central Valley of California. And InSAR, I think it's about the similar cost. So how I was framing that InSAR inversion is also kind of one-dimensional. So I'm basically solving that 1D diffusion equation. So the cost is about the same. And the question is, at that scale, do we really want to use all of 1.7 million time series, or integrate that into a scale of, I don't know, mile by mile or something like that? So it really depends upon the resolution that you want and the scale that you would want to obtain, I guess.
Okay. And right, so I imagine as new InSAR data would come in, you would keep running these and updating your models.
That's the plan. That's the plan if we can extend this to the scale of Central Valley. So if we were successful, under the assumption, absolutely. That's we may want to even generate a system, automatic system. I think the 6-month interval is because of a DWR paying this company to update that every 6 months. But I think the data comes in much shorter time span. So I think there's a potential if you can update that in every 2 weeks or something like that.
Yeah, cool. That's very exciting. We do have a question coming in from YouTube by Mariana G. Mariana says, hello, thank you for this talk. Can you again explain how you analyze head measurements in wells per cluster? Are the values in your graphs the average of all the wells in the specified cluster? Continues, what should be the characteristics of the aquifers for this InSAR subsidence analysis to be useful?
Right. So that's a great question. And that's exactly the challenge, because the head is also a function of three-dimensional space, right? So in vertical direction, the head measurements can be different depending upon the depth interval. So what I had to do, I had to cherry pick the head level. I didn't average anything. I didn't average any head data, but I had to cherry pick the head data that kind of shows the good correlation with the InSAR data. So for instance, like this one. So I cherry picked this one, but there are many other head data. Well, some head data that doesn't really show the good correlation between this InSAR data and head data. But the challenge actually what we're up against, sometimes we actually don't know what is the screen interval depth is. So you actually it's an unknown information. Where is the head data is coming from? That's another level of challenge that we're up against. But anyway, that's what I have done. And the correlation is because you're expecting some delay, and then you're understanding that head drop in previous years can actually make an impact to the current years. So you're using kind of that physical matrix and then see if you can see some expected correlation. That was how we were sort of analyzing the head data.
So thank you. Yeah, Caitlin, you have your hand up.
Yeah, thanks, Seogi, for a really interesting talk. I was just wondering, in your inversion model, did you include any physics about the materials?
Can you elaborate a little bit more about the physics of the materials?
Like the physical laws, the soil mechanics of the system or the rheology, any kind of that information, was that used in the model?
Is that for the airborne EM inversion or the InSAR inversion?
For the inversion to fit the changes in head to the InSAR data.
Oh, no, I haven't used any information like that. But the important part of that proof of concept, I used the hydraulic conductivity value, skeletal specific storage, and other information which were estimated from other people at that location. So I think that was actually the critical part. But your point is it's quite valuable, because later we absolutely need to incorporate those kind of physical information about how the water flows and stuff like that. I think some of the location we do need to incorporate that, and that can actually improve these kind of inversion results, I think.
Okay, thank you.
Yeah, we have one more question coming from Mariana on YouTube. So you mentioned we can check your codes, but in general terms, how exactly in the AEM inversion process did you introduce the constraints?
Great question. So I obviously didn't have enough time, so I didn't walk through kind of the math behind. So here's like a kind of simple diagram. So this is kind of the framework of the inverse problem. What we're asking to the inversion, I want to find the model that can fit the Airborne EM data. Plus, I want to put a favor, I want to find a model favoring the prior knowledge. Okay, and in our case, the prior knowledge of the targets. And what we did, we actually modified the norms of the objective function. And that kind of gives us ability to make a sharp resistivity contrast if the physics says there's something, because there's something anomalous. Or we can actually make the clay layer thinner, by changing this norm. So we're changing the distribution of the resistivity. By doing so, we can actually impose, okay, we're looking for a much thinner clay. So that was sort of the general idea that we put, general constraint that we put to incorporate the prior knowledge of the targets.
Oh, that's cool. I thought it might have been something like the petrophysics guided inversion.
That could also be included. But yeah, the technique that we used was the LP norm inversion. So by changing the P value of the norms, we're changing the spatial features or distribution of the models. So by doing so, we were able to incorporate those prior knowledge. The petrophysics guided inversion could also have a pretty big potential to do a similar ideas, but that was not the case for this.
All right, thank you. Do we have any more questions for Seogi? All right, so I guess we can wrap that up for today. So thank you, everyone, for joining and listening to Seogi's great presentation, both on the Zoom chat and also on YouTube. And yeah, thank you for the questions, and thank you for Caitlin for hosting.
Yeah, thanks for Leo and Caitlin for inviting me and hosting this.